Hi. So today we're gonna see another interesting topic, and this topic has been running on my mind of late. The the main thing which I noticed recently is people around me use containers all the time. They just boot system, and then the first thing they do is open up a container and then run everything in a container. Why should you even use a container in the first place? Do you actually need them, or what has happened in the past few years or a few decades that has eventually made people start using containers? Is it always the best idea to use a container, and what was that before container and everything? I had all these questions, so I wanted to make a video and then explain what happens behind the scenes in a container, and I wanted to make and to explain containers aren't magic, and then I want to brief about what hypervisors are, and then from where we have evolved in terms of virtualization, and then and now we are at container and we have even moved forward. We'll see how the virtualization has been evolved. And especially I wanted to focus on uh, we had this whole buzz of virtual machines that people spin up, and then now this whole buzz of containers. I wanted to see what exactly this virtual machine, and what are the hypervisors, what type of hypervisors are there, and then we'll see in which cases hypervisors are better and which cases containers are better, and then we'll see how this virtualization has evolved and so on. Let's get started. This is the starting point. This is bare metal. So before everything, every all these technology exists, that is VMs or containers and everything, we just have this physical server, and then we deploy our code in there. That's it. I think this will work, right? What will be the problems if we do this? What are the advantages? So first we'll see what exactly bare metal is. So we have this physical machine, and then we run a bunch of application in it. So each of these applications will have its own libraries, and then since there is one machine, the machine will have an operating system, and then underneath this operating system there is a physical hardware. People often confuse about running multiple applications in one machine. When when we coin this term bare metal, people often think that there is one machine and there is one application. It's not true. Actually, you can run multiple applications in a machine, but this can lead to a bunch of complexities which we're gonna address now. So first, what are the advantages of doing this? You have this physical hardware, and then you install some operating system like an Linux or Nix or whatever, and then for then you will install all the application libraries. Suppose there is this Python app and there is this Golang app. You install all those libraries in it, and then you run these applications separately. So what is the problem in this setup, or what are the first? Let me try to explain what are the advantages in this. The setup looks super easy. I think this is the first advantage for me. All you need to do is just run the application, just like how you run in your personal machine. How do you run in the dev environment? You just install the library and then you just run the applications. You do the same here. This this is the most simplest thing. This is, if you want to deploy something, you just deploy it in in a physical server. I think this is the that's why they call it as bare metal. It's just this physical order and underneath it, and then you just deploy application. Okay, let's see what are some other advantages in this. So this setup will give maximum performance because there is no hypervisor overhead. When we when we discuss about hypervisors, you will understand what I mean by hypervisor overhead. There is no hypervisors and everything. Then all the resources are available to the OS and the application below. So this setup is not bad setup. Since we this has been there from the 50s and 60s, doesn't mean this is a bad setup. This is very ideal for certain systems like just database. You just want to run a database, you can just run. Or if you do some kind of HFT here, you can get it right. You just wanted to maximize the hardware use, and you know that there'll be like a application or a tool that might run, and if you are sure that the application would 100% utilize the resource, and you exactly know how the application uses the resources, then this is a very good way of deploying. And another advantage is it has very low latency. Think of it as, because since the number of layers in here is too low, after physical hardware you have the OS, and then next layer is your application. Then if you install a very lightweight OS and a well optimized OS, then you can see that the number of layers in between in your physical hardware and the application is too less. So that means you will have a lower latency. There are better approaches as well, but this is, and the another huge advantage is it is very cost effective at low scale. When we discuss about hypervisors and in the future, there is this type of hypervisor called type 1 hypervisor. To just manage the type 1 hypervisor, it is very expensive. Over a point of time, it gets very expensive. So if you are just wanted to run one small server rack, and you have only workload for that one small server rack, you should go with this approach. There is nothing wrong in picking up an approach. So the main idea of me doing this video is that this bare metal or virtualization approach is not the bad approach, whereas the using of a container and then doing things as they do today by containerization and so on isn't the greatest approach all the time. So I just want because it is very specific to your use case, and understanding the use case makes you pick the better approach here. So these are the advantages of using this bare metal. If this bare metal has these many advantages, why there is virtualization and why we have evolved from this bare metal? As much as this bare metal is good enough, it has a lot of disadvantages as well. So what happens is, since one physical hardware has one operating system in it, it has low resource utilization. That means you have one application that runs in Linux, and you want another application that wants to run on Windows. It is not possible here. So all you can do is boot up another bare metal and then put in your application to here. So if we have used some virtualization approach, we could have squeezed both these applications into the same machine, but because of this host machine having only one operating system, we are forced to use another physical machine to run this application too, which is why it is a very low resource utilization. So because of the same problem, we have this problem of scaling, because if you have like 100 application which runs on different OSs, then you need to boot up that many machines, and setting up involves maintenance and whole bunch of problems. So we have the scalability problem here, and there is another scalability problem as well. We call it as dependency hill. Suppose you have this application A which wants some package of version 1.1, and then you have this application 2 which can only run on version 1.3, and we have this application 3. We assume that a package C isn't used in application 1 and 2. What happens is, we might delete this package C, and this application 1 and 2 might have used this package C which we don't know. If you have 10 machines or a machine or two, you might recognize that some package has been used in some other application and so on. Suppose you have like 1000 machine and use Python and and you assume that you haven't used Python in 999 machines. So you think that only this machine was using Python. Now I don't need Python and I remove the Python here. What if that some random machine like 234th machine is using Python? You can't handle all those scenarios, right? And another problem is, suppose you have some package here which use like version 1.1, and this applications 2 works only in version 1.3. Then what do you do here? You need to upgrade this to 1.3 such that it accommodates both application 1 and application 2. And upgrading this version to 1.3, you need to again retest this application such that it works fine in this 1.3. Usually most of the package has this backward compatibility. Suppose you use some feature that is been part of application 1.1, and the support has been removed, or that for that package in version 1.3, or that function in version 1.3. It usually doesn't happen that they have some kind of backward compatibility, but there is always a possibility that they revoke that in version 1.3. And what will you do? You need to upgrade this to 1.3, and then since if you upgrade this to 1.3, you should make sure that your application is now code needs to change so that it accommodates this updated version. These are some of the problems. Because of this, the deployment time is lot longer, the testing is lot exhaustive, and you can do just limited automations here. What can you do? You can just see, and there is this choice of automation is too low, because it is more difficult to integrate with our cloud style provisioning and all these DevOps workflows and so on. So as much as it has a lot of advantages, it has all these disadvantages. If you have some of the use cases which will go through the same kind of difficulties, then it is better to avoid this approach. And if you just have one single application, you wanted to host that application and then move forward, then in that case this bare metal might be helpful. So how did they solve this problem? You have like 1000 instance, and you need to run multiple OSs in different application. How did they solve? They brought this concept called virtualization, which is the next evolution here. So first let's see what virtualization is. Suppose you have a machine, have an OS on something, or a network, or a storage device, or a OS. So you create a virtual version of this. That process is called virtualization. So what you can do is virtualization, we separate out the operating system out of the physical hardware, because you see in this bare metal, this physical hardware is tied up with the operating system. So you can't separate this operating system out of the physical hardware, because if you want to do so, suppose you have this Linux operating system, it is tied with this physical hardware. So if you wanted some Windows operating system, you need to boot up another machine, because this operating system is always tied to the physical hardware. Virtualization helps you to split this up and separate this operating system out of the physical hardware. We can do virtualization not just on OS, you can do it on network, storage device, so on. So now what we are going to do is, we have this physical server, and then we split this operating system out of physical server. So by doing so, now it is not bound to have one operating system. So it utilizes the same physical server, but now it can have multiple operating system. Like this can be a Linux, there can be a Windows. You can see here, there is a Windows, there is an Ubuntu, there is Arc, and so on. So this virtualization helps you to achieve this. So now you solve multiple problems which bare metal has. The first problem which we discussed is Linux and Ubuntu and so on. Now, since you have like a separate OS which runs in the same physical hardware, so now this operating system is split into multiple pieces, and each pieces will have its own binary and its own application, and so on. So it solves this problem of running multiple applications in the same physical hardware. It has its own kernel, own operate since it has its own operating system, has its own kernel and own so on. So we can now utilize the physical hardware as much as possible. Earlier we need to boot up newer machines to do this, but now one physical hardware we can have multiple operating systems. So virtualization is of two types. They broadly classify as type 1 and type 2. So this type 1 hypervisor is called bare metal hypervisor because see the structure here. You have one physical server. So you have one physical server and then you have something called an hypervisor here. This hypervisor helps you to do all these magic. It's just a software layer on physical server. Now having this software layer enables you to use multiple OSs. And so hypervisor is just a piece of software or a firmware which runs on this on top of this physical server. The place of this hypervisor depends on the type of virtualization. So it's just on software or a firmware which runs there, which helps you to run these virtual machines by abstracting the hardware. So this hypervisor helps you to do the segregation, helps you to pull out operating system out of this physical server, and you can run multiple operating systems securely and efficiently, and it is all thanks to hypervisor. So what this type 1 hypervisor does is, this is the base architecture of this type 1 hypervisor. So what you do is, you have one physical server here. On top of that you install this hypervisor, and then on top of hypervisor you install all the operating systems, and this is the main difference between this type 1 and type 2 hypervisor is there is no OS layer in between physical server and hypervisor. So you just install this hypervisor on top of physical server. So look at this diagram. So there is physical server and there is this hypervisor. You install multiple operating system on top of hypervisor. What happens is, since there is no operating system in between this physical server and hypervisor, so after install you need some kind of a management console to manage this hypervisor. Suppose if we have this operating system, like how we have, what you can do is you can just log in and then you can just click multiple buttons and then configure all these things. That's technically type 2 hypervisor. So you can just log in and do all those stuff here. But here, since there is no operating system in between this physical server and hypervisor, at max what this hypervisor does is it just gives a bunch of IP address through which can be accessed through the managing console. So what we do is, we install this hypervisor here in between on top of physical server, and then when you try logging in, at max it gives you some IP and then very minimal information. So what you need to do is, when you install this hypervisor itself, it comes along with a managing console. Software for managing console doesn't mean it just gives you some console. This managing console is some other computer or machine where you can install the software. Like how you install software for the hypervisor, you install this managing console software. Now since it exposes some IP, you can manage this hypervisor through this external console. So what we literally do is, instead of this, if we have this OS layer in between this physical server and hypervisor, we don't need a managing console because we have this proper GUI in the operating system or something. From there we can proceed, we can install a bunch of OS and then move forward. But since this is just on top of physical layer and you have nothing more than this IP address or this address, so what you do is you just manage all these hypervisors, that is provisioning of this OS, Ubuntu, Arc, and everything through this management console. That's the reason why, even though this is a very fast method, because there is you keep adding layers in between physical server and other layers, it just takes time, right? Since this is very lightweight and it has very minimal stuff which you can do, that is just exposing this IP, and the maximum configuration is done through this managing console. This is extremely fast, and this setup is very common in huge organization. You see in this movie where there is like an infinite number of racks lying there. It's all based on this type 1 hypervisor. So similar to this setup, we have this another rack and another rack and so on. Every one of these racks are installed with the same software here. Every hypervisor on the physical server exposes this IP, and through this you manage them with the help of management console. What all can you do with this setup? There are a lot of stuff which you can do. One major stuff you can do is, suppose you see this there is this you have this Windows Ubuntu in this machine, and you have just Ubuntu in this machine, and you have nothing running in this machine. This management console helps you to move stuff from one place to, since operating system is outside of the physical server now, we detached it out. It is possible for us to move it from one place to another here. Suppose this server has reached 80% of its CPU capacity or something, and this has like, since nothing is running, it's like 10% of its capacity. So what you can do is you can just, through this management console, you can just move this Windows to this server, and the percentage decreases, and then this is increases, so that you get it right. You can now utilize your racks better. Not only that, there is this plethora of things which you can do here. Suppose there's another very important thing which this type 1 hypervisor allows us to do. It is called over provisioning these hypervisors. Let's see what's that. So what this not everybody allows you to do over provisioning. Make sure you buy an hypervisor that can be over provisioned. So suppose over provisioning refers to a situation where you can allocate more virtual resources than what the physical server can actually deal with. Suppose this guy has like 4 GB RAM and 200 GB memory. What you can do is you can allocate 2 GB here, 2 GB here, 2 GB here. So you tally this, it is 6 GB of storage that you have allocated here, but your actual physical server can handle up to 4 GB only. You might have this problem, you might have this question, but how it is even possible? What will happen if all reaches 2 GB? That's the case where you need to make sure that it will never reach that 6 GB, because since you have just 4 GB here, you can't give more than what you have. So then what is the use of over provisioning? Suppose you have the data that you are 100% sure that it won't cross 4 GB, like combining everything won't cross 4 GB. In an ideal case, what you would do, suppose you have this 4 GB of space in 4 GB RAM in your physical server, you would give 1 GB to Windows, 1 GB to Ubuntu, and then like 2 GB to Debian. So what will happen if If Windows reaches this 1 GB, you have nothing to do. And what happens if you reach this 1 GB in Windows, but this Debian at most use 1 GB at a time. There's a case where Windows is using 1 GB of RAM, and then this Debian is using 1 GB of RAM, but Windows has maximized because we have allocated just 1 GB to it, but this Debian has another 1 GB free which is not utilized. For this exact use case, what we can do is we can over provision Windows. Sorry, we can over provision the hypervisor. Suppose if I have over provisioned it to 2 GB, 2 GB and 2 GB, what happens is the moment it reaches 1 GB, it still starts using the resources until it reaches 2 GB. But we are pretty much sure that this Debian machine won't reach this 2 GB and it will at max be 1 GB. So that the additional 1 GB which earlier wasn't used is now given to this Windows machine. So if you are 100% sure that not all the resources will max out and it will cross this physical server's 4 GB, you can over provisioning hypervisor. Even in the worst case scenario, what will happen if this max out like 2 GB, 2 GB, 2 GB? You always have this management console managing this server, and you can anytime move this to some other physical rack. So this is one key feature that type 1 hypervisors provide. Unless and until you buy this, it won't be available. So you can over provisioning more than what you have, and you should be sure that it won't cross the limit. So that by over provisioning, somebody is underutilizing the resources. That resources is given to this guy. If everything is over provisioned and everything is full, the management console will take care and it will move to some other server if it is been properly provisioned. But you will collecting data for a month or a 2 month or 3 month, you will know that how much some servers use and some application use and some application doesn't. So with that you can have this rough idea on which one to over provision and which one you don't have to over provision. So this management console is mighty expensive, like mighty expensive. It is like few $1,000s for just one server and so on. It is very expensive. But the main advantage is, since there is no OS layer in between, this is extremely fast and you have all these gimmicks in managing the servers. And this is very, very common in industry because you have this whole bunch of server racks and one console just manages all of them. There is another type called type 2 hypervisors. This is very common in our personal computers and so on. So there is this physical server and there is this OS which has been installed. Like for example, we have this Mac OS installed here or Windows installed here. Yeah. We have this Windows installed here in our laptop, and then what we do is we can install this hypervisor, example VirtualBox. We install this VirtualBox here, and through VirtualBox you can install this whatever OS you want, and then you can use them. So it's just you have this computer, you have this VirtualBox software which is your hypervisor here, and then upon opening you can install any number of OSs in it and then go use those OS. This is very common in domestic use, but the problem is this is a bit slower because you have this. You can see the problem, right? There is this physical system and there is this OS running, and then on top of that there is a hypervisor, OS, and then hypervisor, and then on top of that you are installing the OSs which you want. The problem because of this, this type 2 hypervisor is a bit slower when compared to, is less efficient when compared to type 1 hypervisor, and there is one huge problem which can happen. You have this Windows OS which needs like 2 GB of resources, you Ubuntu needs 1 GB, and then like Debian needs 1 GB. So assume that you have utilized this 2 GB of Windows, and you have utilized every RAM that has been provisioned for this virtual machines. What this will do is it'll pull things from our base OS itself. Suppose this base OS runs out of resources, this will crash down, and then everything will crash down. That is one major problem in this type 2 hypervisor. But if you want to learn how different operating system works, or if you have a Windows machine, if you want to try out Ubuntu on it, you can just install a virtual box app, which is the hypervisor here, and then you can install any OSs you want. To some extent, a Docker for Windows, which will come later, which containerize, has an hypervisor layer of Linux on top of it, because a lot of flow on how these containers are created, a lot of internals of these containers rely on few important components of Linux. So when we come to this container chapter, I would explain how containers work, and I'll see how this container and this type of hypervisors are in some way linked in one or two use cases. So this is this type 1 hypervisor and type 2 hypervisor. So now, until now, what we have seen, first we have this bare metal server where we just run multiple application here. Now we want some more control of operating systems, and then inside the operating system we need to run the containers, we need to run the application and so on. So for that control, we brought in this whole new concept of virtualization, and we have this two types of virtualization, type 1 and type 2. Note that here if you are installing Windows OS, that means that the Windows OS has its own volumes, and then it has its own kernel, and it has its own stuff. Similarly for the Ubuntu and whatever OS you are installing. What is the major advantage here and disadvantage here? Advantage is very clear. Now with the help of this hypervisor and everything, you can run multiple application, multiple OS. It is more isolated when compared to this container and as well as this bare metal. But there are a few disadvantages as well. It is too heavy because multiple OSs have been installed. You have this multiple OSs, and suppose you wanted to run an application or an n number of application, and each application doesn't need its own OS, and this is a really bad idea, because each one has its own OS, it drinks a lot of RAM because of the same reason. Multiple OSs, everything runs individually, and because of this, this whole setup is very heavy. Type 1 is a lot lighter when compared to type 2, but still this whole setup is very heavy. Suppose if you have this use case of that you don't need different OSs, you just want one operating system, but you want the application level isolation, then this virtualization, this hypervisor, this whole thing is a bad idea for you. Then how are these problems solved? So now I have this unique problem, that is I want application level isolation, that is my application needs to be isolated. It needs to run in its own packages. Which is solved in virtualization. But I have another problem. I don't want different operating systems. I just want one operating system. But I want application level isolation. Here there is no application level isolation because it just uses these common packages. It is possible for you to install two different versions of the same, like suppose you use Golang, it is possible to install two different versions of Golang, but eventually maintaining them on everything is tedious. So I want application level isolation, but I wanted to use just one operating system. So one major problem with this virtualization and hypervisor and so on, suppose you switch off and you want to switch it on, because it has to spin up all the operating systems again from scratch. It takes a lot of time to boot up, and I want something very light. I wanted to isolate the application. It should have its own bunch of packages. It needs to have its own bunch of files and so on. How do I do that? So this is where container comes in. From the explanation which I gave you, now I think it should be almost clear that the container is not some next level evolution of virtual machine. Virtual machine has its own use cases, and bare metal has its own use cases. Similarly, container has its own use cases. Let's see what the containers are. You have one physical server, and then you have one operating system installed here. On top of operating system, you install multiple containers, and then there is this one container engine that's been running. So suppose you have this Golang app, and you have this Python app, and you have another Node.js app, and another Golang app, which is a very old app, a old Golang app, a new Golang app, a Python app, and a Node.js app. What you can do is you can take up all the dependencies needed for this Golang app, all the files needed for this Golang app, whatever it takes to run this Golang app at application level, and then package it together in form of a container. Similarly, you can build another container with the old Golang app with its own old dependencies and whatever needed for that application to run, and then form another container. Similarly for Python and Node.js and so on. So now you have these 4 different containers, and all these containers run on the same operating system. We run this container with the help of this container engine, and then what this container engine does is it helps you to run all these containers, all this code on top of this operating system. So this is a very unique use case. You can see people use containers left, right, and center, but it is very ideal to use container in this following scenario. You don't want a separate OS, but you want this application level isolation. That is, this Golang shouldn't disturb this Golang, or this Python shouldn't disturb this Node.js, and so on. And in this use case, container is a very useful tool to do so. People always confuse that. Even I have once or twice used this term interchangeably, that container as Docker container and so on. Container doesn't mean it is a Docker container. There is always this, when people mention it as containers, they think it is Docker container. Docker is just a tool which helps you to build this image, and then it gives you this container engine, and then it just gives you, and then it uses this runtimes underneath it. Suppose there is this container D, and then run C, and so on. So it just writes a wrapper on top of this and acts as a container engine which take this images and run, and that's it. So you can write your own tool to just create these images, run it, because all these commands are OS level commands. It is there in the operating system. Most probably this is running. Mostly it is running on Linux. So because Linux has all these commands which has been included long time back. So container doesn't mean it is Docker container. Docker is just a tool which does this, and Docker has this whole bunch of registry where you can share these images, download the images, and then do and so. There is another tool called Podman which does very similar things and so on. So what container does is it just packages everything what is needed for this application and then just isolates it from the other applications. So how does this container work? Is this container some form of magic? Because you can clearly understand how this virtualization and all those stuff works underneath, right? You have this physical server, you have this OS, you have this software called a hypervisor, and then that you install this Windows, and for each OS you give some kind of specification, and it like this RAM storage and everything, and then you spin this up. But how this container works internally, it looks like a magic. You just package the application in it, and then you just this container engine does some magic, and then suddenly all these things are isolated. That is, this is not linked to this runs separately, this runs separately. You mount some volume, even that is isolated and everything. How all these things happens? Let's I wanted to go a deep dive into it, but since this video is already long enough, I will just go and explain it in a very shallow level, and I will make some other video just explaining the container under the hood, how the container has been implemented. I will try explaining each and every step which goes underneath, but as of now I will just explain this container internals on a shallow level. There is just they have this four important components for any container. These four important components combine together to form the container which we use. So these four things are just Linux building blocks. All these four things are individually available in Linux kernel, and these tools utilize all these four things together to form this container. So containers doesn't emulate hardware like how VMs do. Instead, they share this host kernel, and the host kernel is Linux here, most probably. So they just share this Linux, but they isolate other processes, because application level processes needs to be isolated. That's our main goal. So how this is happening? How application level isolation is happening? This this container primarily relies on these four building blocks, I would say. First one is union file system. So this union file system is also called as union mount file system, because we are merging multiple layers of file system together. So I wanted to deep dive especially on this union file system, on this overlay FS and so on. But as of now, let me explain the high level of this union FS. So what happens is, when you create this Docker image, you always notice that there is this layers of images that's been formed. Suppose you create a container image. We'll take Docker for example. You wanted to install Python app, so that will have certain packages that will be in a layer, and then you want to copy file from one place to another, that might be a layer. You want to build this, that might be a layer. You are just adding in the secrets, that might be a layer, and so on. You can see there is this layered architecture, and then there is one concept called copy on write. So let's first see what union FS is, then what overlay FS is. So it's just an, if this is union FS, this small part is overlay FS. So it's just a Linux implementation of this union file system. So what happens is, we can just there's a folder A, and there is this folder B. We can call this as upper, you can call this as lower, and then this is upper. So what happens is, when you mount these together, that is, if you use Linux, when you overlay these two folders together, what happens is it just merges in form of layer. So this is lower, this is upper, and the result is we can take this as folder C. So the folder C, after mounting folder A and folder B with overlay FS, overlay file system, or if you since I'm using Linux, even Docker uses overlay file system underneath because it runs on Linux. So it just merges these two things together as as file C. So what does this merge means? And why is this merge important, and why are we using this overlay FS? So suppose A has a file A1, and then B has a file, same file A1. So lower has a file A1 and upper has a file A1, then lower has a file A2 and upper doesn't have file. So what happens when we merge these through? First the ones in the lower comes in A1, A2, and then since on top of this upper gets placed, since A1 is repeating, that is that file is repeating, it gets replaced with the one in the upper. So this is the eventual file which we get here. So we have this A1 from the upper and then A2 from the lower. So now what happens when I delete this A2, or when I write something in the A2, when I modify something in some file in the lower region? So now we have this A1 and A2, and this A1 is from the lower, and then A1 is from the upper and A2 is from the lower. I try modifying this A2.text which came from lower. What happens is there is this copy. Suppose A2.text has hello world in it. So what I'm doing is, now I am modifying this hello to hi. So now A2.text has just hi. So what technically happens is, this is not deleted or this is not modified, whereas a copy of this A2 with this modified file is being added to the upper. So any changes you make on the lower file, it just keeps writing on upper. So if you have the same file in both the lower and the upper, then upper wins. That is, upper files comes in. That this whole idea of this upper file taking is more taking precedence over lower file is called copy on write behavior. So what happens is, the files in the lower are just visible. You can't like technically edit the file in the lower region. If you try to modify something in the lower region, the updated file gets stored in this upper region, and it is not edited in the lower region. So you can see this stack of stuff which keeps happening. So why do we do this? Why do we need this overlay FS? This tremendously improves the build time of creating the containers and reusing the containers. We'll take one example here for the reason why we are using this file system. Suppose we have we do some download here, or we have this file got one.txt in lower, and then we have this file 2.txt in upper, and then we have this 3.txt in the lower. Now after mounting, we have this 1, 2 and 3 here. Suppose it's been layered. So this is from this is 2, this is 3. So this is from the lower, and this is from the upper. So now the next time when you modify something, like when you add this 4.txt, or when you modify this 2.txt, some text out of it. Since you have this all the layers being stored, you can just reuse this layer. So 1 and 3 remains the same, and then you just add the modified 2 here. Suppose you modify this 1 here, you have this modified copy of 1. Suppose when you are reverting back, since you always have this one copy in this lower, it just easily gets reverted back. So this whole principle is called copy on write, and this is the whole idea behind this overlay FS. This is the file system that this containers use, and especially Docker uses something called this overlay file system, which is the Linux implementation of what I told you. And the next important thing is namespace. So, like I told, we have this one single operating system here. Then how do we isolate the applications? It is because of this namespace and the C group. Namespace just provides the isolation for the resources, so that the container just thinks it has its own resources. Even though some containers just share this operating system resources, we this uh, Linux kernel has this particular namespace feature which helps in to which will provide this isolation of resources, so that it can think that it has its own environment. Suppose you have this process IDs, you can isolate the process ID. You can have a separate process ID for this container, separate process ID for this container. You can have this isolate network stack for this container, for this container as well. Similarly, inter-process communication, isolate host name, and then you can isolate user IDs for both the containers and so on. So technically, even though you use the same OS, at software level you can just isolate all those things and emulate this whole isolation concept. So because of this, each container has its own set of namespaces. So these namespaces has these all bunch of properties like this process IDs, net IDs, IPC namespace, user IDs, and so on. So it just feels like running in its own system. Even though it just uses the common operating system, it just feels as if it runs in its own system. We can fake this as if it has been running in its own system, but how do you actually monitor the resources, or how do you actually limit the amount of CPU it uses, amount of memory it uses, amount of IO it needs, and etc. This is done using this C group. So you keep it this way. Namespace, you are just tagging these guys and differentiating between different containers, and then C group, you are just allocating the required resources for all these containers. Suppose like 20 percentage, it is restricted to use just 20 percentage of the resources, like 10 percentage of the resources, or like 512 MB and so on. So if it exceeds its limit, the kernel can throttle and kill the processes. Remember this. So using namespace, you just give the namespace for the individual containers. It's some kind of giving their unique IDs, so that it thinks as if it is some individual system, and then with the help of C group you can just allocate different memory, different CPU, different IOs for individual containers. All these are through software. All these things happens via our Linux kernel. That's why this whole containers are operating system level virtualization rather than hardware. So, and then the final runtime engine. So it just uses the command like container D and so on. Like this, there is this another command called run. Think so. It is called. It is called as run C. It is that there is this container D, then there is this run C. There is this low level tool that just creates and runs container. So this Docker has this. Suppose if it is a Docker container engine, it's just a wrapper over these Linux commands. So it just creates all these images, and then this runtime engine just runs the container. I think this would be a good primer on differentiating between what you need and what is available in the market, because doesn't mean it is been there from 1940 it is a bad idea, or doesn't mean this is been used everywhere this is the best idea. Based on your use case and based on what they offer, you can choose whatever tool you want or whatever way you want to implement this. I think that's the whole idea of this video, just to uh, say that some might need containers, some might need virtualization, some might just use bare metal and so on, and it's all highly personal and depends on your use case. I hope you like this video. I'll see you guys in some other video. Thank you.